wanted to first thank those of you who have come out to our speaker series this year. We've had 7 terrific speakers and good attendance at all of them. And I think it's been a really nice addition to the intellectual community here at Rossier. So I'm hopeful that we'll be continuing it next year, and probably you will be hearing from me with a solicitation for recommendations relatively soon. And so thank you again, and I'll introduce Mary Helen Imordino-Yang.
Thank you, Morgan. Thank you for hosting this series. It's been a really wonderful addition to the climate here. So I don't want to take any more of Jay's time than I possibly can avoid. But he's, I just want to say, a really special person, both personally and academically for me. He's really one of the first people who built the field of neuroimaging and developmental neuroimaging. He spent 24 years at the NIMH as the head of pediatric neuroimaging there. Before moving, he says that the emperor of pediatric neuroimaging, before moving to UCSD last year.
Yes.
Yeah, last year. He's really the person who did the really groundwork on human brain development in health and disease, and is now looking at genetics and neuroimaging approaches to try to understand healthy and diseased human development and how we can connect these issues to societal issues. Next week he's off to Boston to be an expert witness in the Boston bomber trial, and he's done a lot of work on with the American legal system, also looking at the role of adolescent brain development in the crimes that adolescents commit and the kinds of punishments that are appropriate for them. So without further ado, I will introduce Jay. Thank you.
Thanks for that. Thanks for letting me come talk to you. So I study the teen brain and mostly like what I do, but when I tell people what I'm going to be talking about, I tend to get unsolicited feedback, like maybe a very short talk. Found one. Contradiction of terms, or along this line of search for the elusive, my next talk will be the Loch Monster. But in fact, teens do have brains. The technologies that have come along in recent years, such as MRI, we've been able to, the first time, look under the hood at the living, growing teen brain. And so if you remember nothing else from this talk, this is the one point I'd like to make. Not only do teens have brains, but their brains are doing very well. They're different than the brain of a child, and they're different than the brain of an adult. But without those differences, we wouldn't be here. And so they've really been exquisitely forged by evolution to have certain features. Behaviorally, this shows up in, these are the so-called big 3, increased risk-taking, increased sensation-seeking, which at first sounded to me like the same thing. It's subtly different. And a move away from parents to peers. And the reason they're called the big 3, that they've all been replicated over 100 papers. It's not only in humans, all social mammals do these 3 things. So I think it's really kind of ingrained in our biology. We're not going to stamp these out, we're not going to limit it, and we probably even shouldn't. But we do want to keep them non-lethal. We want to people get through this period alive for the best of their options. And it's always speculative to say, like, why are the evolutionary forces, but one of the ideas is that this allowed us to leave home, which is pretty irrational, right? Your parents, they love us, they feed us, they protect us, we have our back. So why would you leave? To go off to school or college and stuff. There's a lot of reasons not to, but it worked in terms of our ancestors who left were more likely to avoid inbreeding, healthier genetically. I don't think it's like a moral thing. It's just sort of the evolution and genetics favored people who would take the risk and seek the sensations to leave home. Kind of close to where I used to live, less so now. The Smithsonian, the Hall of Human Origins, is I think for me a very interesting exhibit. And one of the things that's not particularly featured is this sort of panel on the floor by one of the exhibits looking at the relationship between climate change and increase in human brain size. And the subtle part of this is what correlated with the last big increase in our brains 500 to 800,000 years ago was not the harshness of the climate, but the change itself. So before seeing this, I was like, yeah, times got really tough. Only the most clever amongst us can survive this cold and find food and being able to stay alive and reproduce. But this is different. This is that the key was being able to adapt to these rapid changes. So everyone in this room had teenage ancestors whose brains were very good at change and adapting. And it came kind of close. It got down to about 50,000 people in terms of it before rebounding. And so this has been, I think, the key in terms of the protracted development of the human brain. Before I forget, just all the slides are available to anybody who would want them. You can use about it. It's like if I go too fast, I just realize that all the slides are be there. So it's amazing how much can be discerned from teeth. So like teeth are fossils. Even the teeth in our mouth right now are technically fossils. So they're mineralized cells. And looking at Neanderthal teeth, they're kind of like trees and tree rings. Like this was a year of rapid growth, and this was a year of less growth. But the key here is, well, this is often spun as surprisingly rapid growth in Neanderthals, but I think it's backwards. What's surprising is how slow the growth is in humans. We're the outliers as a species, like by far. No others is even close to how long we're with parents. Even across corvids, crows, other species, the longer you're with your parents, the bigger your brain, the smarter you are. In terms of food gathering and stuff, it's sort of an interesting relationship. So if you find a fossilized tooth of a 12-year-old Neanderthal in a cave, he's much more likely to be with his kids than his parents. So they didn't really have teenagers. I mean, they lived in the second decade, but things were speeded up. There's only humans, somewhere between 500 and 1 million years ago, we had some kind of stretched out, protracted maturation. And it's good and bad, but the good is we keep options open. We don't have to lock it in early. We can live on the North Pole, we can live on the equator, we can live everywhere in between. We can even live in outer space, for a little while with technologies that our brains develop. But the key is that we're built for change. It's very protracted range, which is really the essence of a lot of the work that I do. And more recently, we've had a huge change with the digital revolution. Revolution is kind of a hyperbolic term in terms of like it's thrown out there. I really think this, when we look back, will be a revolution, 500,000 years from now, in terms of just dramatic change in the human condition. And how much of our time is spent now with ones and zeros. So the digits are not these; it's the ones and zeros, as we're doing at this moment. The PowerPoint, presentation, and this has dramatically changed the way that we learn, the way that we play, and the way that we interact with each other. Here I say since Gutenberg's popularization of the printing press, I'm not sure what the right benchmark, but it's pretty remarkable in terms of the amount of time that we spend. And I've kind of focused on adolescence at this interface, but it's not just adolescents. Really young kids too, those can meaningfully interact with iPads. And older people can go on Facebook and communicate with their grandchildren and do this. So it's not just adolescents, but adolescents are kind of in a sweet spot. They're old enough to master these technologies, but they're young enough to embrace the novelty and the change. The little kids, they're good at the iPads, but they also like swipe refrigerators and objects that that aren't in the iPad. So I've been fascinated by this interaction between this highly adaptable brain that's built for change and this huge change in our lives, which often kind of boils down to, is it good or bad? In terms of, and like most interesting questions in science, the answer is it depends. It depends on the type of interface with social media and stuff, how much, to what degree. But that's what I'm interested in, like the nuances of this. In what ways is it good? In what ways is it bad? How do we optimize the good? Minimize the bad? Because it's here to stay. This genie's out of the bottle. And as adolescent psychiatrists, it's striking. This is their world. This is the world of not just sort of kids that are ill or asocial and stuff. It's it's their world, and many of us who work with adolescents, it's not our world. We don't get it. It's not just a matter of sort of knowing who the hit bands are or the linguists are. It's this fundamental part of their lives. And a lot of people my age and therapists is sort of like, yeah, we kind of gloss over that because it's not how we do things. So one aspect is learning in terms of, I just think this is huge. Like the greatest minds on our planet and stuff is there, free, a click away. It's amazing. I mean, it bothers me. I have 22-year-old, 20, 17, 15, and I'm like, aren't you guys like, don't you think this is so amazing? Whatever, So no, it's like we have access to information that kings and queens just haven't had. It's incredible. And it's only getting better. The TED Talks, the Khan Academy, MOOCs, it's just phenomenal. The ability to reach each child where they're at in terms of development and guide them along electronically. So then one of the issues as well is it's not a matter of enough facts and figures, it's too much, kind of signal to noise and this gusher of information. How do you find the gems? How do you find the good stuff? And is it kind of all a mile wide, inch deep? And I think it can be, but it doesn't have to be, right? Actually, if you click and follow the links, you can do deep scholarship. You can get quite a good depth. My kids are told don't use wiki and stuff, but we use it all day long, and stuff. And yeah, some of it's not great and stuff, but a lot of it is. It's surprisingly quick. And so this is, I think, one of the great challenges because the education system, I wouldn't say can't keep up, but they're not keeping up in terms of the whole new world. In terms of the challenge won't be memorizing facts and figures. 30 seconds, you can find how high any mountain is or how long a river is and stuff. That's not going to be the useful skill. It's how do you use information to solve problems, and how do we teach kids to do this? One aspect inherent is multitasking. So this is 2010. The newer data I think will be even more compelling with more mobile devices. But about 11 hours of a day we're with the screen. 8 hours sleeping, how many hours sleeping? It's a lot, right? And about 30% of that time is more than one device. So you're doing homework, but you're also checking Facebook status and listening to iTunes, and eating, kind of things. A lot going on with multitasking. So that's one of the concerns and questions. These are two twins that have been in our study since they were little girls.
I'm working on my Spanish homework, chatting. I'm working on my English homework, Facebooking, trying to figure out math, doing Spanish, but then I'm also doing Facebook, listening to some people, and Giedd. I'm doing 2 different Spanish homeworks, and I'm texting. And I'm checking my math answers.
So Rocky and Anika, they're like great kids, right? The one like mission to use this, they're now in the colleges of their choice. And this is an unusual life. This was in Maryland, but I think in a lot of parts of the world. I mean, this is business as usual now. Their homework's online. It's not even that they're just playing games and stuff. It's mixed in with their school and entertainment, their social interactions. And so how do we study this? And multitasking is actually kind of easy because you can have people in a scanner. You can say, listen, is this word a noun or a verb? Something even not that hard, while you're doing a driving simulator and things. And so you see all these non-additive effects where driving simulator might increase blood flow 5 to 8%. Noun or verb might increase 5 to 8%. Do them together, 5 plus 5 is 10, no, it's 50. So you have these huge interactive effects where basically it's like driving drunk to do multitasking. And this is something our brains get better at, but it makes team dividing and multitasking particularly risky. The play in terms of the games are really, really fun. As a dad, I can attest to that, getting game for my kid and being up till 4 in the morning myself this morning. But it's a super competitive, $40 billion industry. Some top people are doing this. The R&D is second to none. Even greater than the military in terms of number of people hours dedicated to this. They're they play the dopamine reward system like a Harvard. They're really fun. And you could say, yeah, but it's like a couch potato, like you're not running, jumping, and playing, but that's not even true anymore either. You can have connect and refit and interact, and you can make it as challenging physically as you want to change the settings. So it's so powerful, engaging. Like, how can we harness this? How can we use this? I don't think there's so much that it's like bad for your brain to do these things. There's so much competition. There's so much more fun than homework. That's, at least in my house, that's the battle and stuff. How to balance that? What's the right amount? Is it some hour? Probably not. It's probably for a child. But there's also like the sex exposure, violence. So the trick is not to come across sexual stuff online. It's going to happen. Ads and stuff like that, and violence. So since 2002, the amount of time spent with violent video games is up fourfold. And the degree of violence is only limited by our imagination. It's not completely over the top. And the sexual content, for me, it was like that weird National Geographic issue that would come every now and then. And now most people's exposure is online, about a quarter of internet traffic and stuff. So this is like eroding the moral fabric of our nation, all of that. So all these things you would like predict, but the real world data is the opposite. So unwanted pregnancy, sexually transmitted diseases, 47-year-old. Real world violence, 49-year-old. So it's puzzling, it's like people saying like, well, yeah, they're not mugging you, they're in their basement. They're playing games and stuff. And that may be actually part of it, but it could be something more profound too. We're working through sex and aggression in virtual environments, because those are also us in the human condition, sex and violence. Those are the prime directives to stay alive and to reproduce. But if it was the other way, it would be all over this, right? It was, of course, this is the problem. So I'm puzzled. I'm advocating, more sex and more violence in video games, less on the streets. But it is intriguing, and I think there's this kind of mentioned history of this same things being said about paperback novels and TV and radio. So every new thing that comes along is, this is horrible. It's going to wreck everything, and so far it hasn't. Social interaction, again, the quarter of all internet traffic is social media. I think it taps into something really profound and deep in us to connect. This idea of a global community where 17 to 21-year-olds, they know more about what's going on in the world. They're more less like provincial in terms of people might have different food and dress and cultures or religions and stuff, but fundamentally we're a lot more alike than different. We still laugh at the same cats playing the piano or whatever the current sort of memes and stuff are. But it's kind of interesting, just like as a kind of a offshoot of this in terms of that adolescence. A lot of it is about peers and sharing experiences. It's a smaller world in that sense. We have more common experiences, and the optimist in me thinks this is a good thing. Like we might have less prejudice, which is largely ignorance often. We don't understand other people, and so hopefully that'll be a good outcome of this. It takes a lot of time if you let people go online during lectures and stuff. If they're not on task, which most of them aren't, it's mostly social media that they'll be doing. The issues of cyberbullying they're nuanced, and bullying happened before the internet, and it's still happening stuff now. But there is a certain degree of accountability too. Is like what happens in Vegas stays not on the internet. I mean, it's traceable. It's not nearly as anonymous as people think. So when it happens, it's tragic and horrible, and makes the headlines. But I don't think it's like drummed up a lot more business, so to speak. People have other ways to do it. But more fundamentally, it's like social interaction, share the same temperatures, smells, touch, all these things, and so much of the task of adolescence is social interaction that there's just something not right about this, in terms of that. Like Grandma Giedd, just it ain't natural. Sort of like there's got to be something wrong. With this people like 3 feet away from each other, Facebooking and instead of talking stuff. But I don't know. So like reading's not natural either. Reading's like 5,100 years old. So throughout most of our human history, nobody read. And so, 10,000 years ago, that's not that long ago in evolutionary terms of hunting and gathering berries. Now most of us spend a lot of our waking hours with words or symbols. So I don't think the fact that it's quote, not natural is a kind of compelling argument. But for me, it really is the key of all this prolonged plasticity during adolescence. It's a double-edged sword. It creates a lot of opportunities for learning new skills, for wiring the brain in ways that are going to serve us well, and also vulnerabilities. And so my work is fundamentally this. I'm trying to explore the path. How does the brain grow? And the first 13 years of my research was almost exclusively just that. Just sort of, how old are you? What's your brain like? And then around 2002, kind of switched to mechanisms and influences. So I started doing twin studies. About 70% of all my scan sets have been twins, healthy twins of people with illnesses, to try to, now that we have a rough outline of the path, what matters, what nudges it for good, for bad, what can we do as a parent, as a society, as a teacher, as a clinician or therapist to change this. So at the NIH, we had people, this is very non-creative actually as a place of creativity, but just come to the NIH, get your brain scan, we'll get your DNA from blood, saliva, or skin cell, we'll ask you how you're doing at home, at school, at work, and then come back each 2 years. So we had about a quarter typically developing singletons, a quarter typically developing twins, and the other half from 30-some groups, autism, schizophrenia, ADHD. So this is kind of just going right to the bottom line of what we found for the last 25 years. So the first thing was that the brain doesn't mature or grow by getting bigger and bigger. And at first that was very disappointing. So the brain's this big, you can do arithmetic, this big algebra, this big calculus. That was sort of our mindset. We're going to watch the brain grow and as we got smarter. But by age 6, 93% of adult science. It's like watching paint dry. It's like 3 decades. I was like, and it was a kind of a somewhat of a surprise in terms of because your head gets bigger, which we know from the deep science of Nike and stuff. The hat sizes, they have data on hat size. So your skull gets about 2 inches bigger for boys and 1.9 for girls, but it's the skull, it's not the brain. It's literally the bone. So your brain isn't changing that much in total size, but it changes by becoming more connected within itself and more specialized. So I just will touch upon both of those. The connectedness is reflected in white matter changes, which come from these cells called oligodendroglea, which sounds fancy, just mini branched loop. In terms of, like an octopus will send out these tentacles to wrap this fatty kind of material around the axons, and it greatly speeds up how fast the information can flow. It's literally like insulation, like a copper wire has that little rubber part of it. It's the same idea. And white matter is up, and away. So it goes up to the 5th decade in women, the 4th in men. As long as you don't have multiple sclerosis or things like that, white matter will increase. So about 100 times faster with myelin than without the actual signal. Because what happens is it hops between these gaps. And so the electrical signal, as it hops along, it's really efficient, because what happens for a signal is these gates open up, and all the positive ions outside now can rush in, and that's what makes the electrical signal go. But you have to then reload that. You have to pay back, move those positive ions back up, and it takes energy. About 20 to 25% of all the energy that we use in our body is that, reloading these membranes. But with myelin, since it kind of hops between these little gaps in the myelin, you're able to just reload at those gaps. And so you can reload 30 times faster. 30 times 100 times speed, 3,000-fold increase in bandwidth. So it's not subtle. It's what makes a lot of our human thinking possible. even Drosophila have similar thing. It's not myelin, but they kind of have a wrapping from another brain support cell and stuff. But nobody has it like humans in terms of the amount of myelin, the amount of that we can move things around quickly. But more recently, we found that it's not just pedal to the metal, how fast can we move information, because it's all about the timing. That's not the side dish, that's the main course. That's what information is encoded in the brain. It's the pattern of fighting and the timing. And it's exquisite. I mean, like, in order for a brain cell in the front part of your brain to get information from the visual system in the back, from the auditory in the middle, from the emotion in the center, it has to arrive within a 50 millisecond window. All the yays, all the nays, add them up, should I fire? At that point, it's a yes, no, fire or not. But that's like, it's amazing it ever works in terms of, because that information back doesn't have to go faster than the middle, and so the myelin is involved in this just exquisite timing, which is like the key aspect of it. The other thing that's more recently appreciated, the myelin then releases molecules that prevent plasticity. They prevent further arborization. That's the bargain. That's the trade-off. That we get faster connections, but fewer connections and less plasticity. So having grown up in North Dakota, a pretty rural community, it's really a good place to fly because all the roads are perpendicular. It looks like a giant chessboard, from above. And it's a quarter-mile intervals. You can get anywhere in a quarter-mile pretty directly. But then the roads that get used a lot become paved. Or between major grain centers become like multi-lane highways. Now you can zoom down them faster. They're not gravel roads, you can go fast, but you have to wait for the exits. You can't turn off every quarter of a mile anymore. And that's sort of the trade-off we have. The circuits that we use and work and lead to positive outcomes, they'll have changes, the synapse and myelin stuff, they'll get faster, but we pay for that in terms of plasticity. And so the white matter changes are about 1% to 2% a year, but at the local level they can like double in size in a couple months. And so we're trying to get an idea for like where, when, in terms of this idea of sensitive periods for learning languages or math or morality, in terms of can we link these times of explosive growth in the brain to educational opportunities. Haven't done it yet, but that's one of the goals. But the idea is integration. And so the different brain parts are like letters of the alphabet, and all the letters are there by about 8 months. Hippocampus development reaches a certain level. But what happens then from a baby to a child to a teenager to young adult, these letters get formed into words, the words into sentences, the sentences into paragraphs. And so that's what's changing in development. So it's not just white matter, it's more microscopic, long-term potentiation. You can see under the microscope the synapses, EEG coherence in one part of the brain is electrically active, what other parts of the brain rise and fall with that. Similar for fMRI blood flow, when one part is experiencing different blood flow, what other parts are going in the same or opposite directions. This idea from Hebb of cells that fire together, wire together, but now we also see fire together, wire together, grow together. I'll show some data on that in a minute. Another way to be connected is that certain brain regions or even circuits are affected by the same environmental or genetic factors. And so in that sense they're connected, and I'll mention that a bit as well. But the math for it comes down to this idea of graph theory, which...
Line up. Sing something with a little bounce in it.
It's a small world after all.
No, anything but that.
So I hope I didn't violate some copyright laws, but this is official now. It's the most annoying song of all time. It passed Barney for #1 of all times. But for brain imagers, it's this idea of a small world network. And so this would be, back to North Dakota again, I go to Germany or someplace. And they go, oh, you're from North Dakota, do you know the Johnsons? And I go, yeah, I do actually. And it's, oh, a small world. That's where that kind of term is like, you know somebody who knows somebody and degrees of separation. And so a lot of this came from this book by paper by Strogatz and Watts in terms of of looking at the internet and how the internet can survive a nuclear attack and how do you wire things together. And that this idea of a small world network, a very unsatisfying solution. It's not sort of neat and tidy, it's not symmetric and Euclidean and stuff, but this idea of like how things are connected to each other in nature and biology. And what was really striking was that the same principles that held for how to build a robust computer network also worked for ant colonies, for the formation of galaxies, for the stock market, for plane travel. Just like incredibly universal, the same math, the same solutions. That was like, wow, that's like really unexpected and surprising. So we've benefited enormously from all these other fields, from economics to astrophysics to pure math to computer science in terms of applying it to brain. Because anything can be a node, it can be a quark, it can be a galaxy, it can be a neuron, it can be a hippocampus, it can be, and an edge is any connection. It could be an axon, but it could also be a statistical correlation, any sort of connection. So as long as you have a node and an edge, you're good to go. And the math for this was actually worked out by Euler, probably the most prolific mathematician about 400 years ago in Kaliningrad. And they have these 7 bridges, and the idea was you have to cross each of the bridges once and only once without backtracking. And so they sit in the center of this park and watch the tourists try to do it. It's impossible. But you can do it with 6, so it's not obviously impossible. But he developed the math for dealing with nodes and edges, and it kind of just laid silent for 400 years before Strogatz and Watts did this, and now it's kind of all the rage. So what I wish I could understand better, it's really kind of taken over the field, because now we can go back to the same images that we had all along in this example. Child with schizophrenia. So I have brains of child with schizophrenia and brains of people without. Can I tell them apart? Barely, not really, not robustly. So the same images, no new scans, no anything, using the graph theory stuff, now they separate nicely. So going back to that metaphor, it would be what's different in schizophrenia isn't the letters. The whole literature, all the hippocampus, it's 2%. But so there's a whole literature on that. And in fact, for schizophrenia, it's not even the words, it's the sentences. Kind of a second order down the line is what's different. But this is exciting because it gives us a whole new kind of look at old data, and this also related then to looking at this idea of fire together or wire together, grow together, with the default mode network, which is just when your brain's at rest, what parts of the brain rise and falls together with blood flow or EEG. And so what we find is that EEG is like milliseconds. fMRI is 3 to 7 seconds, it's blood flow. So the same kind of networks hold different parts of the brain, but also not for seconds or milliseconds, but for decades. And so we look at what parts of the brain grow together in terms of have the same change over time in cortical thickness and surface area and volume, and we find the exact same circuits. And we also find them for genetic studies of multivariate analysis, what parts of the brain rise and fall, the same genes or environment. So it's converging nicely. There's sort of circuits and circuits within circuits and meta circuits, but the whole kind of field is kind of moved away from where's the hole in the brain to where is the circuit changes, what circuits are changing. So just as one example from many, we can look at 2 parts of the brain that are involved in vocabulary. And the tighter those parts of the brain grow together, the better the vocabulary scores. Schizophrenia, ADHD, autism. So that's kind of the white matter story. Throughout the teen years, we get more white matter, more connected. The brain is better integrated. The gray matter as
The brain grows like a tree. First, there is a flurry of growth. Then unused branches or pathways are pruned. And it is this pruning that gives the tree its shape for the future.
So one, admittedly condescending to this audience, but this is the Zitz cartoon comic strip. I don't know if that's popular out here and stuff. But they provided these videos for us to sort of interact directly with the students. Because it's really empowering, actually, in terms of that. This idea is that now the brain overproduces, and then they fight it out for survival. And it's how all complexity in nature arises, all complex systems. And really, I mean, it's evolution. It's the engine of evolution: overproduce and non-random elimination. So that's but people often think of, oh, the brain's maturing, it's getting bigger and bigger. But it's more like, you know, Michelangelo's David emerging from the marble. It's becoming more specialized. And it's supposed to. That's not pathology. I mean, it's supposed to do that. But as it does it gets smaller. I mean, you're specializing, you're pruning. And so it gives us another way to look. Then what do we mean by maturing? And so what happens is, because maturing isn't getting bigger, by 12 it's already maximum size. So we have to think of another way of what do you mean by maturation, because the brain is changing from conception through death. And so we kind of have this notion the brain's going to increase during childhood in gray matter and density of receptors in so many measures. There's just this build-up phase. And then fierce competition, it's going to go down. But obviously it can't keep going down forever. There'll be nothing left. So it levels out. And what we're capturing then is the leveling out. So when does it sort of stop changing so much? So these colors now, then blue is when it levels out. And so what we see from ages 4 to 25 is where the red circle is there. This part of the brain, the prefrontal cortex, the latest to turn blue. And this is sort of less shocking now, but at the time we were like incredulous. So this doesn't really turn blue till about 25 to 30. That's too late, right? You've already chosen your spouse, your career. I'm not sure about California, but yeah, it's just like it's just like it's just like as an adolescent psychiatrist, we're like, should we study people till 16 or 18? By 16, they're winning medals in the Olympics, and they're big and strong and smart, and maybe only because of the Industrial Revolution that we even are, having this notion of adolescence. So it's really if you go to the airport to rent a car, you have to be 25 or else. So we're like, oh, Hertz says all scientists. And we kind of joked about it, but it didn't go away. They do have tons of data. 24-year-olds cost them more than 54-year-olds. Their vision's better, their reflexes are better, they do better in simulators. Almost everything you measure, they're better. Tolerance for heat and cold, resistance to cancer, just right down the line. It's like, they should be at totally top of your game. Morbidity and mortality go up 300%. Number one, by far, car accidents. If you're a teenage girl, you die half the time in a car accident. Nothing else is even close. The only other thing in double digits is like prostate cancer, 85 to 95 for men. But it's not. I mean, it's just like, as a parent of a 22-year-old now, it's scary, right? And on the one hand, it's low, right? The mortality is low, but still, it's like suicide and homicide are 2 or 3, depending on the year and how you do it. All the top 10: judgment, decision-making, emotion. And so this is like what Ron Dahl calls the paradox of adolescence. Everything should be at its best, and it's not. And what's not, I mean, I don't want to overplay this. It has been overplayed and stuff as well. I mean, it's not all about these colors and stuff, but this idea that part of the brain that's involved in the hard stuff, not doing the immediate impulse, long-range planning, controlling the impulse, the social brain circuitry, which is huge for adolescents. This idea of time travel and mental time travel, in terms of we can consider past, present, future for making decisions. That's that part of the brain, the prefrontal cortex. Karl Popper, the philosopher, our hypotheses die in our stead, so that we don't have to fall out of the tree, we don't have to get hit by the car. We can run these scenarios in our mind, and as we go through our probably, maybe even into the 50s or 60s, we're better at running these scenarios. Maybe that's kind of part of wisdom and judgment and stuff. You can consider more alternatives, but mentally, in your mind. And so this is a part of the brain, again, that's not broken. It's not like gone, but it's not as good as it's going to get. And that's why about it's not as good as it's going to get. And thank God, right? We wouldn't be here. If this part of the brain matured, really fast, we'd be the Neanderthals. whose brains are actually bigger than ours. They're about 13% bigger than ours. And they survived in really harsh conditions, but they didn't have a good plan B. Their tool use didn't change for 200,000 years. I guess we were like smaller, more nimble, but so this isn't a bad thing that we kept these options open. It's also where when you multitask, this is where it gets bogged down. And multitasking, we can walk and chew gum and stuff, and this is, you're listening to a physics lecture in your right ear and English literature in your left, these kind of things. You can't really do it. There's Marcel Just at Carnegie Mellon calls it a multitasking tax. You can't do it, obviously, you do it all day long, but there's a tax you pay every time you switch in energy, and you can't really get around the fact you can't do a whole bunch of things as well as you can do one. But you can do it pretty good. And so where's this trade-off? You can look at your email while you're listening on the phone. We all do it all day long and good enough. How often do you need to be 100% at your best, and maybe never, or maybe not often. But this is a big issue anyway, because the development of this area, maybe we can get better at multitasking if we practice it, and better at certain ages than others. What matters? Does anything we do as a parent, just playing a musical instrument, just doing sports, just doing video games, bacteria, viruses, second languages, what matters? What matters? And we have this 1-2 punch, overproduce, and then find out what if something goes wrong. So like in autism, if the brains are larger in the first year of life, there's like too many competitors for these limited spots, and it overrides the usual checks and balances. But this is like a paradigm for understanding development, health, and illness, this whole process of overproduction, selective elimination. And that backdrop, then, one of the striking things is this maturational mismatch, would be one way to think of it, in terms of the prefrontal cortex, 25 to 30, again, not absent or broken, but still improving, and this part of the brain, the limbic regions, really being intensified, activated at puberty, which is also oddly biologically, from 8 to 15 is normal puberty, a really broad range for something you'd think nature would have constrained a bit more. But these limbic structures shown here in kind of a little bit darker orange, the caudate looks to me a little bit like a dolphin leaping out of the water. So at puberty, literally at puberty, not age, the hormones of puberty, so all these changes in dopamine and serotonin, norepinephrine, reward system, it's just like really tumultuous in time. And puberty may be actually getting a bit earlier, worldwide, controversial, but possibly. So you have this gray area here, this difference between the early activated limbic system and the later sort of let's think this through, let's think of the long-term consequences. One of the most robust behavioral measures is that we're more likely to choose larger, later rewards as we get older versus sooner, smaller. And decades long, even if you're at an extreme when you're 14, we'll probably keep changing. So the temporal discounting, delayed gratification. And so this ignition in puberty, the scorekeeping is dopamine. So we make a good decision, those circuits fire, it leads to a good outcome, happiness, pleasure. It tells the brain, good job, whatever you just did, that was the right call, let's keep those connections. You make a bad decision, it leads to pain, unhappiness, dopamine down, don't do that again, that was the wrong pattern, that was the wrong fire. But dopamine is the currency for this, and dopamine is pretty ancient, and it's involved in movement and motivation, in depression, anxiety, addiction, reward, and well-being. And everything that's abused increases dopamine in this limbic part of the brain, in the nucleus accumbens. And this has been a sort of a challenge of Nora Volkow in terms of saying this, but we haven't had anything that's addictive. So an addiction is a pathological relationship with a mood-altering substance or experience characterized by compulsion, loss of control, and continuation despite adverse consequences. So it doesn't have to be cocaine, it could be shopping, it could be other, video games, things like that. We keep doing it, we know it's bad for us, we keep doing it anyway. everything is, it's the same system involved in sleep, in sex, and hunger. It's just like so, so primitive, so basic. But this is, I think, a big part of understanding education and stuff. Well, how do we tap into this reward system? How do we engage the individual through this? So we have this very dynamic time. The reward system is being set, so to speak. And then we have substance abuse that are messing with Mother Nature, in a sense. So biologically, the big dopamine change in naturally is orgasm. So 4.7 folders, but things like ecstasy and stuff, double digits. So you're telling your brain, wow, whatever you just did, that was the best thing you ever did. But it sets the bar too high. And so people sometimes during this time, 15 to 19, when that's being set, a lot of people experiment with drugs or stuff, and then they might go on to college and have good jobs, and everything's behind them. They don't do that anymore. But then they come in, they're 40, 50, something's missing in your life. And it's like, you gotta be kidding, you got a great job, great house, kind of go through all that, who wouldn't want to be you kind of stuff. I know, it's kind of part of the problem. I should feel great, but I don't. And so some of this kind of like sad almost in terms of, maybe that's why they're also successful. They keep pursuing one more degree, one more accomplishment, and that. But so I think it's like this idea of like why people should wait. And so substance abuse wise, I hope prefer people not to at all, but like get to 19, and all the epidemiology is just so much in your favor. Some might be socially away from home for the first year of college. If you want to, you could. But I think there's a biology behind it as well. If you get to 19, if you don't smoke, if you don't, these things. Epidemiologically, things are really in your favor. So my pitch is a little less ambitious. Maybe it's like, wait, like people get to 19. And don't do huffing, right? Which is like sipping glue, inhaling hydrocarbons, the most common form of abuse in the world. Most kids can't afford designer drugs and stuff. But why? I keep thinking about creativity, but I couldn't come up with anything more creatively bad. It goes through the nasal cavity, it kills the frontal brain cells. That's what gives it the alters. It's like don't do that. It's I don't want to do the other things and stuff, but it's like separate. And I think that's a message that has gotten through a little bit. It's not just another way to get high. It's like this is like totally different. Don't do that. So that's like my sort of what's happening. Maybe just a couple more minutes of the twin studies. So here's the path. Here's what's happening. What matters. So studying twins. Again, identical. That's supposed to mean non-identical. Yeah, so we weren't worried. So a couple things from the twins is that these are healthy twins, and so which one is slightly heavier at birth? We can tell 30 years later in their brain. So that's surprising me. I thought things would sort of even out, and one of them's got to be heavier. I thought but there's this really quite lasting echo of early brain development. And then the big question was, what's heritable in the brain? And that turned out to be a completely moving target, in terms of the different parts of the brain become heritable at different times. And at first we thought, yeah, you're a twin, every day is a little bit different. In 4th grade, your mom will put you in the same shirt and you have the same haircut, and then 6th grade, that's not cool anymore, and you start, I'm my own person kind of thing. But every day will be a little bit different. So you gradually drift apart, just not as much. But this was the opposite, that people actually become more alike in their brain in adolescence. And then this is and also in IQ, a bunch of things to do this. And so the idea is, yeah, you're born with these genes, but if they're not active, who cares? They don't matter. But when they become activated, then it matters if you're an identical twin or not. Looking back, we didn't see it coming though. We thought, wow, that's that can't be right kind of thing. So now our thinking is, yeah, it's also these same areas that become more active during adolescence are the same ones involved in schizophrenia, which happens at that time. So it could also be why you're born with these genes, you're born at the risk for schizophrenia, but why does it not show up till adolescence? And people say, well, stress. Yes, it can't be, right? I mean, childhood is stressful. People are in war, their parents, horrible, most stress you can think of doesn't have to happen in adolescence. So that never really, rang true. But so really wondering, so these parts of the brain that become heritable later in life, We want to understand what parts, what genes they are, what circuitry they affect, how it relates to health and illness. But it's a really moving target. Like you say, like, does this gene affect this brain in this way or that? And usually people collapse from 10 decades, from the age of 8 to 80. And it's really like bizarre almost, because age matters a lot. An example of why genes matter: 4-fold increase in violent crime, 8 times risk for murder, 50-time risk for death row. I made the last one up, but just so a person that the Y is the Y chromosome is what accounts for all those risks. And so I've been very interested in this for a while, because everything as a child psychiatrist I see is different between boys and girls. Age of onset, symptomatology, and it's not to like who's the winner, like who does this or that better, but there's a huge clue there. Anorexia nervosa, 10 to 1 female. That's a lot. Autism, somewhere between 4 and 7 to 1, depending on severity. ADHD, all things early in life are more common in boys, but things more common in girls are all after puberty. Depression, anxiety, panic attacks. So I think there's like a big clue here. And so looking at boys and girls, the main thing is overwhelmingly more alike than different. So you show me one of the 10,000 scans I've got, is this a boy or a girl? I can't tell. Under a microscope, I could, in terms of, there's this part of the brain that's like 4 times, it's called the sexual dimorphic nucleus, but this is a microscope, not MRI. So we have all these books of these planetary differences, like board games even, right? Mars and Venus. And so even people back home don't get this, but so I think there are differences, but instead of Mars and Pluto, it's more like North Dakota, South Dakota. It's like really like subtle differences. But the subtle differences are meaningful. But it bothers me when the work is like, oh, like teach all girls this way, teach all boys this way. And it's huge. I mean, it's happening, and it's like, yeah, that's one of 1,000 factors to consider in terms of differences. And so height's a good example. So if you go into high school and say, look, everybody above 5'6", you go to this locker room. Everybody below 5'6", you go to that locker room. Well, that's stupid, right? Why is that stupid? Oh, there's so many exceptions to the rule. Just look around kind of thing, right? That's twice the effect size of any of the brain imaging or any of the behavioral stuff. Height's actually pretty good. It's actually a pretty good. It's probably the most robust, and it's bad. It's not enough. And so it's sort of frustrating especially when the work that you do is sort of misused, for these differences. And I'll just wrap up now. But the other big thing was that we found differences between males and females more in the trajectory, in the path of brain development, than in the final size. It also was the key for looking at IQ and measures health and illness. Almost all the fun stuff that's held the test of time, we found from longitudinal data. So that's one of my rah-rahs. And it's like, oh, we really need to do longitudinal data. And this rapid change, the vulnerability, is quite real. Most mental illnesses happen during adolescence. Not a lot, not many, most. Over 50%. And it's less than 2% of research funding. But that's been another theme. I said, why? Why does it happen when it does? And so in schizophrenia, we have not just MRI changes, all these changes, won't go into the details, but every one of them could be predicted. What if adolescence and health went too far? So I said earlier, we want the brain to prune and want to specialize, but in schizophrenia, this is looking at child with schizophrenia from ages 14 to 17, everything's in the same direction, but it's 4-fold. So you have a 7% reduction, and typically about 28%. To my world, that's whopping. Usually it's 4%. It really is. It's like 4-fold is like, wow, it's like through the roof. And so it doesn't mean that causes it, but it's intriguing. And then about half of what I deal, this is what, at NIH I did deal with insurance, and now so as an adolescent, so about half of it, it's not a mental illness. Unwanted teen pregnancy is not an illness, but it's huge impact on your life, relationships, all these things. And so how do we what does we do with adolescents? We say, oh, sorry, you're not in the book. You can't check this box for insurance. That needs to change. So there's a lot of, is adolescence half empty or half full? The usual thing is that for adolescents, the glass is not only half empty, the water's dirty, the glass is cracked, it's your fault. But fundamentally, adolescents are cool wording. I mean, they get through this. Most of them, they do well. They get past this. There's a lot of a different topic. But yeah, so I'll stop there and kind of cut it close. But if there's any questions, comments, I'd be glad to entertain them. And thank you so much for your attention.
Well, as one of the shortest people in the room, I have a question. So I'm really interested in that height finding because what's interesting is that all the research and what you said today is that brain size doesn't matter and brain size is correlated strongly with height, but then you said height does matter. So can you explain that?
It's a good point, sir. So like size, size of the brain in terms of across species, it does matter. Whales and dolphins have bigger brains and they're very smart and things like that. But within individuals, there's this huge range of people where the size accounts for about 14% of the variance across. But I think it's because like Fragile X illnesses have bigger brains, not better brains. That there's not a great connection between size and ability, sort of within realms. Once if it's big enough, you can do it. But that's been a big change. Kind of everything before was size, bigger, better, smaller, better. And the IQ stuff really showed that, where at one age, bigger was high IQ, at another age, smaller was correlated with IQ. We thought, well, that's weird, but then it happens again and again. It's much more about the quality than the quantity.
So, but you had outcomes that were related to height, which is directly correlated to brain. What's the height factor?
It's a weird. I mean, the height stuff is weird in terms of like people who are taller are rated as more intelligent, more attractive, and more likely to hold political office. I'm actually, there are probably some very interesting social aspects of that, but I'm not sure of the biology behind that. Height and symmetry. I mean, one of the ideas is like for there aren't really genes for being intelligent. There are genes for being dumb. That whatever mutation happened in the past, most mutations only make things worse. But something happened, that actually made us maybe an extra doubling in the cycle. And so that the trick of intelligence is having less bad genes. So the fewer copy number variants you have, then the more symmetrical you are. Literally like your right and left, and the taller you are, the higher IQ, and all these things. But it may be sort of a matter of not having mutations, as opposed to having a gene that is a good gene. You're sort of not having as many bad genes. It's kind of hard to. It's not just semantics. It's not just sort of a matter of saying. Yes.
I'm not sure how much work you've done on ADHD brains, but I was wondering if you could talk about some of the differences between those brains. I've heard that, like EEG coherence, like the firing is off sometimes, or just other differences.
Yeah, one of the things was looking like for like a hole in the brain sort of things, and so in like 300 brains we didn't see that in terms of there's no more often. Oh, sorry. The media not found, but I can show it later. So what happens in ADHD, it's that the frontal maturation is delayed. And that's not like the only thing. It's not like, oh, it's just a matter of delay in frontal thinning. But that's another classic example of one that with the graph theory stuff, it's sort of then how integrated is the brain? How does it tie together? And that's what's sort of missing. But it's really important, I think, that it's not a defect. It's not in any kind of, there's no funny business and stuff. And so it's much more likely sort of a variation that served the group well. So you can say, oh, well, how is that adapted for an individual? But if you have 30, 40 people, it's good to have some percent in that group that are high risk taking, where they might wander off, get lost, never seeing it, but they might wander off, find a water source, or, you know, is it rutabaga, is that edible? Hey Fred, you know, I wonder if that cave's empty. We're behind you, buddy, way behind you. So this idea at a group level that, you know, is adaptive. There's a book called The Hunter in a Farmer's Land that never made sense. Like, oh, we evolved as hunters and now we're farmers. And but if you, like I have ADHD, you know, people, you wouldn't want to go hunting with them, right? Like, especially before automatic weapons and stuff, you had to like lie quietly and wait, you know, for hours at a time. You can't be, you know, floating after every beast that's in our sight. So the idea that it's, you know, adaptive in a different time, I don't think is the way to look at it. But it is the case, you know, like the brain leaps to the most interesting thing in the environment. And you can see that might not have been such a terrible thing throughout most of history, but now it kind of is. It's harder to get through school and stuff. But the fundamental thing, after 300, almost 400 scans now, is like it's not broken in any, you know, conventional sense of that term. It's a variant that still is real and, you know, affects people's hopes and dreams and stuff. But the kind of the whole model of a defect in short person.
So, very small brain, very short, smart person. Contradiction in terms. So, I'm interested in late onset schizophrenia. So, you know, early onset, of course, much more severe when it appears in the LS brain. But then there's late onset, like in the 30s. And do you know anything about why that occurs? Or is there brain structural changes related to that, or is it environmental, or do you know anything about that?
That's a good question. I don't know that as well. For a lot of these things, and like ADHD as well, it's like, about, you know, 10 things have to not be broken. So for ADHD, it's frontal lobe, basal ganglia, cerebellum. Any of those 3 things off, you get the same final common pathway of distractibility and attention. And so I suspect it's that way for schizophrenia as well. To not have schizophrenia, every link in the chain has to be solid. And in youth, one of those links is broken, and that's what leads to it. And in older age, it's a different link. But it's still like in any one of them. But yeah, I mean, it definitely happens, and also the other way people's symptoms can improve later in life as well. But there's this whole kind of LIFO or palindromic last in, first out aspects of brain development. The parts latest to mature are the first to go. And so that's another, you know, theme being explored, where you could look at, do people with childhood schizophrenia and late onset, you know, have commonalities. Yes?
So you talked about how evolution like shaped the adolescent brain partly because of the selective pressure that's on the brain when adolescents leave home. I was just wondering, because there are a lot of different cultures where adolescents don't really ever leave home. They grow to adults, they stay with their parents all their lives, and they live with extended families. So I'm wondering how you think culture plays into adolescent brain development and...
It's a great question. I mean, you know, Mary Helen's done some cross-cultural stuff, but so little has been done, right? In terms of almost all the studies are US, Japan, Germany, now some more emerging in China and India. But yeah, great question. Like, you really wonder how much is you know, biology, how much is social, how much is other environmental factors. And yeah, so sort of dodging the question a bit, but it's not it's a question I've dodged before. I guess it's just I thought about this for some time in terms of how much of the delay in terms of adult role. Because adolescence starts at puberty, but it ends in sort of a social definition, attainment of adult roles. And even since the 70s, that's extended a lot. When we get married, when we have our first child, when we buy our first house and stuff, it's all like 5 years later in the US, and then even in the 70s. And so, like, that's probably not biology, right? In 40 years, biology wouldn't have changed that much. But even across cultures, the big 3 still hold. That people do have increased risk-taking, sensation-seeking, and move from parents to peers. That's been like 80s and culture. So those 3 things do seem to be pretty resilient. But you're right, like in America, so like a virtues, oh, you left home, you got, out of the house, and other countries that may be seen as, leaving your loved ones behind. Yes?
In the video that you showed on how the brain matures, besides the prefrontal cortex, it looked like the superior temporal cells
Yeah, good
also.
catch. Yeah, all the exactly. Yeah, superior temporal and another quote high association area. Mm-hmm. And so the parts of the brain that integrate information from all the rest are the latest to mature. And it's like a tie actually between the superior temporal. So the ones that first are life support, heart rate, respiration, and then it's the five senses: sight, sound, touch, smell, hearing. And then it's like looks like a duck, walks like a duck. The kind of the expanding hierarchy, and the quote high association areas are the latest to turn.
Were you surprised that the prefrontal cortex wasn't more frontal, more anterior?
Yeah, because I would have probably thought orbital frontal as well would have been my other bet, and so yeah, it's definitely not a perfect story in that sense, and I'm still not sure why.
We probably should end here.
Okay, yeah.
Join me in thanking.